Welcome to the short discussion on the topic stresses in axially loaded composite bars. This is also part of the unit 1, namely stresses and strains in the strength of materials 1 course. By the end of this discussion, I am expecting that the learners will be able to explain the concept of axially loaded composite bars and able to calculate the stresses in the composite bars subjected to the axial loads. So let us look at some of the examples of the composite sections. So here we can see the concrete encased into the steel section, right? So many RCC members will be seeing that a combination of steel and concrete, right? Either concrete is encased in a steel beam, or you can say in a steel reinforcement, the concrete is poured out, and you will get a composite section there. And here you can see concrete filled steel tubes, right? Or even sometimes some kind of shafts made of some metals, they are fitted into one into other one. They will be inserted into the inserted one type of metal is inserted into another type of metal. So all these are comes under the example of composite sections. So now our question is this such composite section. For example, here RCC may be even subjected to other kinds of forces such as bending or even shear forces. But here our discussion is limited to only when these members are subjected to axial forces. Okay. So when such a member which is subjected to axial force, how to calculate the stresses in such members. So let's proceed with the discussion. Now let us first try to understand what is a composite bars. Just to before getting into the point of analyzing them. So let's see what is a composite bars. A bar made up of 2 or more members. Right? It can be either minimum of 2, and it can be more than that even. So 2 or more bars of equal lengths, right? And preferably they may be made up of dissimilar materials and rigidly fixed with each other, and they will be behaving as one unit when it is loaded. So it may be subjected to some kind of extension or compression under that loads. So these altogether we have been set 3 conditions. They must be having more than 2 or more bars having equal lengths, made of dissimilar materials or different materials having different X modulus of elasticity, and they must be behaving as one unit. Such a members we refer as such bars are called composite bars. Now for the analysis of such kind of composite bars, usually just 2 conditions are sufficient. What are those 2 conditions? Is so because they are acting together, if at all these members, depending upon the type of load, it may be a tensile load or it may be compressive load, it may be subjected either compression or tension. So if at all any compression or tension caused due to the external loads, that must be equal for both the materials. So that extension or compression each bar is equal. Right? The same thing, because the length is equal, the extension or compression may be even taken as a strain. Right? So the strains in the both materials are equal. That is one condition. Right? Based on that we can formulate an equation. We will be seeing for that. And another condition is that whatever the load acting, total load acting, or total the composite section is subjected to, that particular load will be shared by both the materials. Doesn't matter how many materials are there, all those materials will be sharing the load, right? In proportion to their ability to carry the stress and their cross sectional area, right? So let's know those two conditions we'll just put in a formulation, right? So let's say there are two metals which are composite bars because they have been satisfying all these conditions, having the same length, made of different materials, and they are fixed. They are acting as a common unit, right? So now you can treat this as consider this as a composite bar. Now let us look at the details of the particular composite section. There are P is the load acting on the composite section, and L is the length of the composite member, and the areas are different, right? 1 and 2, the areas are different. The Young's modulus is different because they are made of different materials, right? So that's the there is a known data for us, one sense. So probably we may be asked to find how much load that each of the material or each of the bar is carrying, or how much stresses each bar is developing. I may be interested to know. For all those cases, these two equations are sufficient enough to uh, help in finding those. Let's see. So as we have told, there are two conditions. One is the load will be shared by the materials according to their ability to carry the stress in the cross-sectional area. So they are shared. First of all, the condition is that the load will be shared by the both materials. So if this is 1 and this is 2, the total load acting on that is P, and load carried by the one member 1, bar 1 is P1 and this is P2, then P equal to P1 plus P2. This is one condition. Okay. So this same condition we can express, we are explicitly in terms of loads. That one can be even written as the load can be written in terms of stress and cross-sectional area. Right. So P1 may be even replaced by sigma 1 A1 and P2 because we know the stress is equal load by area, and that from that we can just replace P1 with sigma 1 A1. But this we are writing in terms of stresses and cross areas, which are here the cross section area is known to us, right? Then similarly stress in the bar 2, we can even transform that into the stresses and areas, right? So ultimately the equation will be transforming like this: P equal to sigma 1 A1 plus sigma 2 A2, right? Since the ends of the two bars are rigidly connected, so that I am going to the second condition. What is the second condition we told? If at all the bar is subjected to the compression or extension, that must be same, or strain must be same. So here we can see that strain in bar 1 is equal to strain in bar 2, or extension in the bar 1 is equal to extension in the bar 2, right? So in general, what is extension in the bar formula? We have know the formula like delta of 1, let's say delta of 1 is equal to delta of 2, and that one we will write as P1 PL by A, the standard basic formula, right? P1 L1 and L2 of course same, so I am not writing L1. So but the cross sectional area different and the Young's modulus may be different. So in that case, this is the equation P2L by A2 P2. So when you cancel out this what you call length, then you will be getting sigma 1, right? Because P by A refers to the stress. So you will be getting because L cancel out on the both sides. So we will be getting sigma 1 by E1 equal to sigma 2 by E2. So you got this. Now once you got these two equations are sufficient enough to now find out whether the stresses that need to be found out in these materials we can easily calculate, or the load for that matter. Either you can require to calculate the stresses or loads, we can easily do that. Of course, here is a no, small uh, uh, point on the modular ratio, right? E1 by E2, which is called the ratios of modulus of velocity is called E1 modular ratio. This is no, preferably used in RC structure when we are using the working stress method. Is one of the key parameters for the design of the RCC members. Right. So now we got the fundamentals of the composite bars, how to analyze them, or how to find out the unknowns when a composite section is subjected to axial load. So now let's look at a numerical example to make it more clear. So there is a problem here given: a solid steel bar of 30 mm diameter, right, and 2 meters long, passes centrally through a copper tube of internal diameter 40 mm thickness of metal panel, right? That means here one steel one is a solid one and the copper one is a hollow one, right? So here the diameters were given and they are braced, and the tube are braced, ends of the bar and tube are raised together and a tensile load of 150 kilonewton is right, applied axially to the compound bar. So this axial load applied here, and the Young's modulus are, the both materials are given in giganewton per meter square. So we all know that 10 power 3 megapascals may be equivalent to, right, 1 giganewton per meter square, or we can even say um, uh, 1 megapascal. Once after converting into a megapascal is nothing but Newton per mm square. You can write in our convenient units. Right? So find the stresses and load shared by the steel and copper section. So what was asked? Stresses and the load carried. Right? So we will try to solve this particular question just in 2 steps or maximum 3. We can try to solve this. Right? Let's make things in a systematic. So here first of all let us identify what has to be found out. So stresses in the bars is what is required, and the load shared by the steel and copper also required. So here our unknowns are sigma c, which we are calling as stress in copper, and sigma s is stress in steel. Then here the load shared by the copper is Pc and load shared by the member Ps. Right? These are the unknowns that we are supposed to find. And the known information is it is subjected to a common load of total load of 150 kilonewton. Actually there is one more zero here. 150 times 10 to the power 3. So this is the load, and we have the length as 2000 mm, and for steel the diameter is a solid one, so this was given as 30 mm. Okay. 30 mm, and for the other one, for this one, this is a hollow one, this has 2 diameters. The inner outer one is say 50, and why 50? Because we got the inner one here. The data was given in a slightly different way. This is 40 as given. This is 40, but the thickness was given. Thickness of this tube is 5 mm. So 5 mm on this side and 5 mm on this side, together 40 plus 5 plus 5, that comes around 50. So that is the information. So you got this is 50 and outer diameter, which was represented as diameter of the copper at the outer end is 40 and inner end as, sorry, it was reversed there. So this must have been I, because inner it will be always less than the outer. So this is your I, O, BC O. your outer diameter. This is your outer diameter, and so outer diameter is also known to you. So then we can start doing the once the outer diameter is also known. Now you know the total areas, right? Area of the steel is known to you. Area of the copper is also known to you. Right? So almost no, they are comes under the same value. So when you calculate and now convert, here is a very important point. Whenever we are substituting, make it in a consistent units, preferably because we express finally stress in general as in Newton per mm square. Convert the force units to Newton and your area or length units to the mm. That makes the problem simple. So 2000 giganewton per meter square was given, so that you can convert to 200 times 10 to the power 3 newton times. As I said you earlier, this 200 giganewton per meter square can be 200 times 10 cube megapascal, which megapascal also can be written as newton per meter square. So after converting this into the respective units, now you are ready to use the formulation. Just now I told you two conditions are sufficient to analyze all these kind of problems. Right? So what are the two conditions? Load shared by one material is equal to load, so total load acting on the composite bar is equal to load carried by the individual bars. That is P equal to PC plus PS, right? And that is one. Another one is the condition of the equal displacement, right? They are equal strains carried with both. So here, this one, applying the strain displacement, equal displacement first is easy because we get to know all the values because the length here in this formulation, you can straight away because ECs are known to you. You can get a relationship between sigma s and sigma s. See, right? So sigma s is nothing but when you use that extensions are equal, the extension of, because the load is a tensile load, both may be subjected to an extension. Extension of the steel must be equal to extension of the copper. Right? So if that happens, then you will be getting this one. Right? PL by E of this it must be equal to PL by E of that. Because these two are equal, you will be straight away P by A as sigma, and here also P by A as sigma. So sigma by E equal to sigma by E of copper is equal to sigma by E of steel. So from there, because you know the values of the Higgs modulus, one is 2 to 10 power 5 and one is 1 into 10 power 5. Right? These are the values that you got, right, given. So there you can get the relationship here and use the second equation, namely load is shared among not equally, but according to the their capacity of stresses and the cross section E equal to PS plus PC. So we substitute that. You will be getting total load as 150 kilonewtons. Sigma S is the stress in steel, which is unknown, and sigma C, the stress in copper, is also unknown. The areas are both almost same. So now you have the relationship for sigma S and sigma C. Now the equation is converted into single unknown, so you can get the values of sigma C as 70.71, and from the relationship you can get the other stress sigma S as 141. Once you got that, you can get the simply multiply with the cross sectional area. You will get the respective load carried by that particular material, namely steel and copper. That's all about the composite section. Thank you.